Hi, this next project is an indoor air quality monitor. So for years I've had an interest in measuring air quality. For me, one of the things that is interesting is particulate matter, stuff like dust, pollen, etc. I notice I get lots and lots of dust in my computers, for example, in the office. I happen to live in an area where we do have frequent air quality issues due to temperature inversions and whenever there's a wildfire and that sort of thing. So the first thing I did was look for existing air quality monitors. So I've been aware of this URAD monitor for a while. Let me link the URAD monitor page. I basically came across the URAD monitor back when I was interested in Geiger counter projects, because it was originally a radiation monitor, then it kind of grew into being a environmental monitor. I'm not so much interested in the radiation monitoring these days. I kind of played around with that a few years ago and found that by and large I don't see much interesting data on radiation. And if I did see some interesting data on radiation inside my office, then that would be a really bad thing. But what is interesting is other things about air quality. So temperature, humidity, pressure, weird gases in the air from when I'm soldering or 3D printing or something, CO2, stuff like that, and dust, of course. So the URAD monitor, it measures all of that stuff, but it also costs an awful lot for a URAD monitor. So I wanted to see if I could build something with similar environmental monitoring capabilities myself, and maybe it'd be cheap enough that I could deploy several of them, maybe put some inside, some outside, one in the garage, just collect data from different places, see how it correlates. So that's how I ended up rolling my own. Let me pop it open. So basically what I did is I selected this more or less the same set of sensors as the URAD monitor. Just because if they worked for them, they ought to work for me. So here I have the Winson particulate matter sensor. It'll measure PM10, PM2.5, and PM1.0. These are different sizes of particulate matters. I believe it's a laser sensor. Also call this a dust sensor since it's going to measure dust. It does have a little built-in fan. It's got a window. You can't quite see it, but there's a window down here on this side of the case where air is sucked into the chamber and it's measured and then blown out. Also in here we have the Winson CO2 sensor right here, which will measure carbon dioxide. Over here is a Winson formaldehyde sensor, which measures formaldehyde in the air. I'm not sure exactly why that's important. I basically did that sensor because the URAD monitor folks also chose that sensor. I figured if it was interesting for them, maybe it'll be interesting for me. I do think, things like internally like soldering, 3D printing, gluing, stuff like that, maybe we can get some interesting data on the formaldehyde sensor. So these sensors, although they're designed for particular gas, they will often cross-indicate other gases. So if you look on some of the data sheets, you will see, some of the other things that the formaldehyde sensor will cross-indicate. Or when I was early playing with this, I tried breathing on them, and when I breathed out and the formaldehyde sensor showed a raised reading, I wondered, am I exhaling formaldehyde or am I exhaling one of these other cross-indicating gases? And then finally, we have a Bosch BME 680 temperature, humidity, barometric pressure, and volatile organic compound sensor. That's this purple board. It may not be obvious from the photography, from the angle of the camera, but the sensor is angled up about 45 degrees to try to get it into the airstream to get those accurate temperature measurements. Over here we have a little breakout board that I designed and a Raspberry Pi 0W. And the Pi 0W is going to do all of our data collections. And then finally here we have an exhaust fan. I went with a 3-pin fan, which has power, ground, and a tachometer. And then I PWM it to get a certain speed and then measure the speed with the tach wire. Now you might ask yourself, if the Winson sensor has a fan of its own, why do I need a separate exhaust fan? I just had a lot of trouble getting stable temperature readings from this temperature sensor. like the URAD monitor design, I tried even putting it way over here by the fan from the dust sensor, and it still, anytime I close this case up, there's enough ambient heat in here that the temperature sensor would slowly rise. So what I did is I added an additional fan, draw some airflow through here, got some holes in the cover so that there's plenty of room for air to go into the case, just to make sure that air is never stagnant inside of the environmental monitor. The fan is not running at full speed. That would probably be more airflow than is necessary. It's PWM down to a relatively low RPM in order just to get enough airflow to turn over that air in there. So as far as I know, the additional airflow from the fan, it's not hurting any of the measurement in here. I don't know that for a fact. Sort of being a home enthusiast with this, I don't really have the equipment to do calibration and, really scientific testing to see how well this is working out. But I think it's working. So let's take a look. I'm going to pull out the Raspberry Pi just so you can see the breakout board I have in there. So I do have to kind of pull out the SD card so that we can get into it. Move the fan wire out of the way. It's not the easiest thing to get out of there. I did design kind of a tight case here. And let me just put something under here to angle this just a little bit. Okay, there, you ought to be able to see the breakout board. So there's not a whole lot going on with the breakout board. Of course, we have a big header for the Raspberry Pi. We have a power input here for 5 volt DC. There's a transistor. This is a PN2222 that I use to supply power to the fan, so I can PWM that power line. Capacitor here to, give me some clean power. And then there's, all these various breakout connectors. So I kind of use double pin headers so I can double stack these. So a couple connectors over here for the CO2 and formaldehyde. Connector here for the temperature, humidity, and gas sensor. One down here for the dust sensor. One there for the fan. I have a lot of resistors in here. Now these various devices said they were 3.3 volt logic compatible. But still, I like to put, on some of my projects, I like to put these dropping sort of protection resistors, just in case you did something stupid in the programming and set a line as an output when you meant it to be an input, and then you've got a conflicting voltage here and a voltage from the sensor. You don't want to burn out the sensor or the Raspberry Pi. So these are kind of like just idiot-proofing resistors. So, in a final design, those could probably be eliminated. So like I said, a very, very simple board. Let's put it back together. Now, it did take me a couple iterations to get this case design right. So here is one of my earlier prototypes. Originally, I had a lid on it like this one. Actually, I had an even different lid. Originally, I had this solid lid on here. And my thought was that the air would come in down here at the dust sensor and sufficient would blow out up here by the Pi all on its own to turn over the air inside. And that didn't prove true. So at one point I tried adding some more vent holes. That still wasn't good enough for that temperature sensor. It would just rise and rise and rise every time I put the lid on. Then my third iteration was this lid here, which, I stuck a fan to the outside to blow the air out over here by the Pi, and that was when it finally worked. And then, of course, my fourth iteration was the final one where I have the fan mounted inside. So that does kind of demonstrate the value of 3D printing, that I was able to do a lot of trial and error with these cases until I got one that was giving me the sensor performance that I wanted. Without a 3D printer, I'm not sure exactly how I would have gone about making all of these case prototypes. Here's a quick look at the schematic. As I said before, there's not a whole lot to it. First of all, we can delete this part here. This was an optional switching power supply that I put on the board, and I did it in such a way that I could cut it off, and I did in fact end up cutting it off. Switching power supply, additional heat inside the case, decided not to go with that. You can also ignore the encoder. I'm not sure why I put an encoder footprint on the board. Maybe I was thinking at one point I would do a user interface on this, but it doesn't need a user interface. So the main parts, you've got the Raspberry Pi over here, and then you've got all of these headers. So the header for the dust sensor, it's got its power and ground, and a receive and a transmit. All of the Winson sensors use serial, so it's just 2 pins for communication, a TTL level serial receive and a TTL level transmit. As I said before, I've got these sort of idiot proofing resistors on all of the I/O lines. Going down here to the CO2 and the CH2O, the same thing. We've got power and ground, the pinout's a little bit different, and then we've got a receive and a transmit for each one with some of the idiot proofing resistors. The fan connector has a transistor. I originally did a 2N3904, but I think a 2N2222 is probably better current handling than the 3904, so I made that substitution. But the transistor drives the ground pin to the fan. It's driven through a 1K resistor on its base and hooks up to the Raspberry Pi. That pin right there. For the RPM signal, there's a pull-up because it is open collector output on the fan's tachometer. And then it actually does go through one of these resistors over here that is on the encoder footprint and into the Pi. So the temperature sensor is an I2C interface, so it has an SCL and an SDA that are wired up to the Pi. I put protection resistors on those as well. You need to keep those values relatively low. I used like 150 ohms, it works fine. I did put 2 footprints in for the temperature sensor, depending on whether I wanted to mount it facing up or facing down. Okay, I'm going to talk a little bit about the software. So I wrote the software in Python. I made heavy use of a library called PyGPIO, and you can see me kind of using it here with this set mode and these serial reads and opens. And the reason I did that is because we have 3 different serial devices that we need to use. And those are the Winson sensors, the dust, the CO2, and the CH2O. The Pi only has 1 built-in serial port, but you can emulate a serial port using software, and that's one of the things that PyGPIOD does. So way down here at the bottom, this is just the module here that does the CO2 sensor. So it opens up PyGPIOD, and then it instantiates a dust sensor. Going up here, we can see we set the transmit and the receive pins to inputs and outputs. We open the serial read at 9600 baud, and then we create something called a wave. So there's like not actually a serial write in PyGPIOD, but there is this, you can create a wave, like a waveform, and you can put serial data in the waveform. So I created a waveform that requests a sample from the CO2 sensor. And then periodically, down here, we send out the wave that requests the packet, and then we do a serial read. Then there's just a little state machine here that decodes the packet. And each one of these, the CH2O, the same sort of state machine, the dust, similar state machine, each one of those work the same way. Piece of cake. The BME 680, that's an I2C device, and I ended up using BME 680 library that I found on the web. Here I'll link a page to it now. There's BME 680 is pretty complicated sensor. Trying to write that all myself seemed hard, so I just found the library and wrapped it around with my own wrapper. So I've got environmentaling monitor daemon. This instantiates each one of those objects with a reporter, and the reporter is responsible for taking the data and storing it someplace. Collection of reporters I have. Support a variety of things as I was getting this working. So printing to the screen, saving to an RRD, round robin data file, sending UDP to another machine. So originally I was going with kind of a client server thing here, and using Prometheus. Prometheus is a time series database. Coupled with Grafana, you get nice graphing features. So that's all I really want to say about the software. It's pretty simple. I'll put it up on my GitHub repo for anyone who wants it. So here's the daemon sitting here running right now. Um, it's actually doing both an RRD locally and supporting the Prometheus interface. And you can see every 10 seconds it just spits out its data. So we've got the data, it's got a station name, then we've got the particulate matter. There's a PM 1.0, a PM 10, a PM 2.5, formaldehyde concentration, CO2 concentration, humidity, temperature in Celsius, pressure, fan RPM. All the data is there and going out those various reporters. So to look at this, I actually had several different things. The first I did was to try using RRD. So I used RRD for projects a long time ago, basically weather monitoring projects. And RRD has some rudimentary graphing features. So you could see this was like my early experiment. It's probably about a week ago that I did this using RRD. And RRD is a round robin database. It stores data in a round robin way. It creates like average files so that you can have history. It was nice for its time, but these graphs are very limited. They're not interactive at all. To do this kind of a solution, you would like regenerate the graphs when someone refreshes the website. Kind of a 1990s, early 2000s sort of UI. The better thing that I switched to is Grafana and Prometheus. Here we have Grafana. Grafana is a user interface for Prometheus that will graph the data. Prometheus is the actual time series database. You can see here's all of the various sensors. These gaps that you see are when I unplug the unit for some reason. So actually, right here, this little tiny gap is when I unplugged it to do the videotaping in this very video. So obviously when it's unplugged, there's no data. So other gaps were when I was working on it, um, trying out different cases, that sort of thing. So, the nice thing about Grafana is if I want to see a different range, like I can go over here, last 5 minutes. Now I have 5 minutes of data set to automatically update. We will refresh every 10 seconds. Apply. So now in 10 seconds, we should get another pulse of data showing up. There it is. There's our data. So every 10 seconds, we'd get new data and we'd see 5 minutes. I can go to something else. I can go for today so far. So that started at midnight and went through now, which is around 2 p.m. Let's take a look at this. So I've got several graphs here. These four are from the BME 680. So here we've got temperature. Here we've got humidity. We've got barometric pressure. And we've got the gas sensor. The gas sensor is kind of interesting because it doesn't really give us an absolute value. It's giving us a resistance reading for the internal resistor in it via like an A to D converter. And I think it's the Adafruit article says it'll be somewhere between like 0 ohms and several 100,000 ohms. Higher numbers are worse, lower numbers are better. If I opened the window and got some fresh air, the numbers would probably go down. This seems to be kind of the steady state that I'm getting is somewhere around 90K on the reading. Then we've got the carbon dioxide and the formaldehyde. The CO2 sensor, I put this particular environmental monitor together just about yesterday afternoon. And the CO2 sensor needs to run for 24 hours to perform an automatic baseline calibration. And it hasn't run for that yet. So it's giving us data that's not calibrated. What the calibration procedure does is it assumes that at some point during a 24-hour cycle, you'll get down to 400 parts on the CO2. and then it will calibrate the sensor, assuming that low value is 400. So we haven't done that yet. I unplugged the sensor here, so I'm going to have to wait 24 hours after that, and then we'll have this calibrated. I did see with my other one, let's see, can I do like last 7 days? The other one, when I calibrated it, you can see it was working as expected. We were getting numbers around 400 in the middle of the night when no one was in my office. And then once I came in my office, the CO2 would kind of go up like so. And then, when night came, it'd go back down. The formaldehyde, you got to wonder what caused this huge spike here. Was I working with some chemicals, doing some 3D printing, soldering something? I don't know. I'm going to have to pay attention when I do something and see what emits various chemicals. The particulate matter, you can see here, we get some spikes on there. I do sometimes shave in the office, and every time I shave, I guess the razor gives off some particulates because there'll be one of these little spikes on the PM graph. I don't know what caused this big, huge spike here. That'd be interesting to dive into that and find out. And then the fan, measuring the fan RPM is a relatively recent addition. That's why there's no old data here for the fan. And you can see we're getting, on average, around 5,000 RPMs on the fan. And that is it for the environmental monitor. So I'm probably going to deploy 3 of these environmental monitors, one of them in my office, one of them outdoors, then maybe one either downstairs in the living area or out in the garage or something where there'll be slightly different data. Then it'll be easy cut. Then it'll be interesting to compare my data with the regional data on air pollution. So we do have pollution issues in town, often due to the temperature inversions, wood burning stoves, that sort of thing. Be interesting to see if I see the PM spikes at the same time they do. Be interesting to compare the indoor to the outdoor. And it'll be interesting to see the various activities I'm doing in the lab, the soldering, 3D printing, etc. See what effect that has on the environment inside the house. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.